Alright, so let us start with the class today. What we are going to learn today is what is called matrix of a linear transform. Alright. So I have vector space V. Its dimension is, I am starting with, so alright, let it be n. Fine. I have another vector space W, its dimension is m, and T is the linear transformation that I am looking at. What mode is given to me? I have been given A here, a basis, ordered basis, basis of V. I have another basis here which is the ordered basis, basis of W. Want to compute a matrix that represents T. Fine. That is our aim here, that we want to compute this. Fine. So any x here is being sent here as T of x. Fine. Now x in this part looks like x of A, which in some sense is A inverse of x. Alright, in some sense. Alright, it is not exactly A inverse, but it is in some sense this. Here I have Tx with respect to B, and therefore I have B inverse of Tx with me. Is that okay? I want to relate these two. So in the previous one, when I went from A to B, two bases, there I didn't have Tx, Tx was x itself. Now I want to understand these two. Fine. So let's try to understand what we are trying to do. Fine. So I want to look at, want to understand linear transformation. Fine. So let's do it slowly so that you understand it. So when I write T of x, fine, we write it as T of, say, some alpha 1. So let the basis of this be V1 to Vn here, and the basis here be this be, so I think I should put this bracket, so say U1 till Um, fine. So alpha 1 V1 plus alpha 2 V2 plus alpha n Vn. This we saw that this is nothing but T applied to, recall yourself, V1 to Vn, and then it is alpha 1 to alpha n, which was same as looking at T of V1, T of V2, T of Vn, and then alpha 1 to alpha n. Fine. So this is the vector which is x with respect to A. Fine. Now each of these T of Vi, they belong to W. So we can find their coordinates with respect to the basis B. Fine. So again what we have done, we will have to multiply it by B inverse in some sense, and then take out B inverse outside and do the work. Fine. So let's try to understand them nicely, what we are looking at. Fine. So need to find T of V1 with respect to B, T of V2 with respect to B, and T of Vn with respect to B. Fine, this is what we need to find out, and then something will come out here, and then we will proceed. Is that okay? This is what we had done for the ordered basis from A to B itself for the same vector space. So let me try to see it now in a different way. Fine. So what we have is T of V1 is an element of W, implies there exist scalars A11 or Aij or Aj1, 1 less than equal to j less than equal to m, such that T of V1 is equal to A11 W1. Did I write it as basis as W1 or U1? U. Alright, so it is A11 U1 plus A21 U2 plus AM1 UM. Similarly, I can write T of V2 as A12 U1 A22 U2 plus AM2 U11 UM 1222 M2 and so on till T of Vn is A1n U1 plus A2n U2 plus Amn UM. All right. Understand what we are trying to do? What we are trying to do is T of V1, this is an element of W. Similarly, T of V2 will be an element of W. Each of these T of Vn, they are element of W. So I am writing them as linear combination of basis vectors. Fine. Once I have done that, then I can think of T of V1 in the basis B as A11, A21, AM1. This as TV2 with respect to B will be equal to A12, A22, AM2, and this will be T of Vn with respect to B will be equal to A1n, A2n and Amn. Fine. Is that okay? And from there I can build up this matrix that I started with. Fine. So let's do that one by one slowly so that you understand them nicely. You have to be very careful, you have to understand it, otherwise there will be problems. Fine. So when I am writing T of, I think I wrote it as T of V, T of x. I wrote T of x. So T of x was equal to T of alpha 1 V1 plus alpha 2 V2 plus alpha n Vn. By linearity of T, I have here alpha 1 T of V1 plus alpha 2 T of V2 plus alpha n T of Vn. All right. This is what we had, T of V1, T of V2, T of Vn. So again look at here, T of V1, this is what we wrote. Fine. So that there is no confusion for you, otherwise there will be problems. So this is same as alpha 1. Now what is T of V1? Look at what is T of V1. T of V1 was, let's write this as linear combination. So what I have is summation something A here, U I here, I is going from 1 to m, U1, U2, Um. So I is going from 1 to m, that's fine. Look at this, 1 is here, 1 is here, 1 is here, and the first part is changing. So I am writing AI1 here. Is that okay? So this is my T of V1. Similarly, I have plus alpha 2, fine. But then if I look at T of V2, T of V2 is U1, U2, Um. So again Ui comes into play, I is equal to 1 to m, and this 2, the second component is as it is, so I have this. So plus so on, plus alpha n, I going from 1 to m, Ain Ui. Fine, this is what we do. I don't want to get into, so let's understand slightly more now. Now what I have done is that I have written TV1, TV2, TVN in terms of the basis of the right hand side of the codomain. Fine. Now I want to write what are the coefficient of U1. So what is the coefficient of U1? I want to find that. I want to find the coefficient of U2 and I want to coefficient of UM. There are vectors U1, U2, UM with me. I want to find their components, all right. So look at here, this is getting multiplied with alpha 1. So this is getting multiplied by alpha 1, this is by alpha 2, this is by alpha n. So I'll get alpha 1 times A11 here, alpha 1 times A11 will come here, A11 plus alpha 2 will get with A12, alpha 2 with A12 plus so on, plus alpha n will get multiplied with A1n, alpha n with A1n. Fine. Similarly, when I look at U2 here, alpha 1 is getting multiplied to alpha 1 is getting multiplied to A21, alpha 2 is multiplied to A22 plus so on, plus alpha n is getting multiplied to A2n. All right. So understand it nicely here, very important. I am looking at 1. So look at 1 where 1 comes. 1 comes here, 1 is here, 1 is here. So 1 is appearing in the first component, 1 in the first component. Fine. This is U2, so 2 should appear in the first component. Fine. So 2 in the first component. Similarly here I should have, so I can write here is summation j equal to alpha 1 alpha 2 till alpha n 1 to n. Fine. I can write it, so 2 is fixed, so a n j alpha j. Can you see this? So look at again nicely here. I am looking at AM, so AM has to come, so this should be MJ, AMJ. So this M is there, so there has to be this M. The first component, if you see here, 2, 2, 2 here, so this is M, so M has to come, and this alpha 1 is with 1, 2 with 2, N with N. Fine, so N with N. So this is what I am going to get. Fine. So therefore this is equal to, the first part is, fine, I don't know how to write for you, so let me use this notation itself. So summation A1j, so A1j alpha j, j is equal to 1 to n times U1 plus j is equal to 1 to n A2j alpha j U2 plus so on, plus j is equal to 1 to n AMJ alpha j of UM. Fine. So once I have got T of x here as this, now what are these? These are elements of ordered basis of W. Fine. Since they are ordered basis, so Tx with respect to the ordered basis B will look like, all right, it will look like ij equal to 1 to n A1j alpha j. The first element of U1 is this, so you have this. U2 will give me this part, summation j is equal to 1 to n A2j alpha j, and the last one will be j is equal to 1 to n AMJ alpha j. All right, this is what I will get. So this is equal to, look at the matrix product, it is A11, A12, A11 alpha 1, A12 alpha 2, fine, A13 alpha 3 till A1n alpha n. So this is what it is, alpha 1, alpha 2, alpha n. Look at this part, it says A21 alpha 1, A22 alpha 2, A2n alpha n, and similarly the last one is AM1 alpha 1, AM2 alpha 2, AMN alpha n. All right. So I've got that T of x looks like this matrix times this. Fine. So this is equal to, so any linear transformation T of x looks like a matrix A times alpha 1 to alpha n, and this was nothing but A times this vector was x of A. All right. So I do not want to confuse this A with that A. So let me write a different notation here. The notation that we follow is T of A and B here. Fine. So it is T of A and B times x of A. So recall what used to get cancelled out. The top one is to cancel out. So this will cancel out with this one. You will be left out with this. So this is what you are left out with. You want to compute with respect to B. You look at the domain, domain has x A, so A has to be written in terms of B and then you have to compute it. Fine. So let's again go back and understand it nicely. This is the crux of the thing, so you have to be careful. We have got T of AB. What is T of AB? So what was A11, A21, AM1? So look at this part. This was the first row, or sorry, the first column. So TV1 of B is the first column. So I would like you to see here that the first column of T of this is A11, A21, AM1, which is nothing but T of V1 with respect to B. All right. The second column, the first column when I write, it is basically this comma 1 that I am looking at. The second column all right is nothing but A12, A22, AM2, which is nothing but equal to, again same thing, T of V2 with respect to B. All right. So see here, 2 is there on the second part. All right. So let's go back and see here. This is what it is. 2, the second part is the same. Is that okay? So you can see that what we have got makes sense. So what we are doing is, so we wanted to compute T of x. So we wrote TV1, TV2, TVN. This was our x of A that we already wrote here. We have to write this with respect to B. All right. So if I wanted to have this B here, I have to write this with respect to B here. Is that okay? So you are writing B with respect to B means I am writing this with respect to B, this with respect to B, this with respect to B. All right. So it is V1, V2, Vn which are playing the role. Fine. So this is the roles which are coming from here. Fine. So in the nutshell, what I am trying to say is that there is a notion of what is called T of AB. So T of AB means, so what we wrote was T of x with respect to B was equal to this times x with respect to B. So we are saying that any linear transformation from a finite dimensional vector space to another finite dimensional vector space, all right, one finite dimensional to another finite dimensional vector space comes from a matrix. And what is this matrix? T of AB. A is ordered basis of domain, B is ordered basis of codomain. Fine. And so if number of elements in A is n, number of elements in B is m, then T of AB is a matrix of size M cross N. All right. How do you get the sizes? Again, understand, there was a mistake here. All right, should have been A here because X is an element of the domain. So there is a mistake there. So TAB here. So X is an element of A. It has got size N here. So this is an N cross 1 matrix. Fine. This is an N cross 1 matrix. So if I want to multiply these two, N cross 1, so there has to be N columns here I have. All right. This is a matrix of size M cross 1 because B has M elements here. So this is a matrix of size M cross 1. So this N comes from this N and this M will give to this. So it is an M cross N matrix. Is that okay? So therefore I got this as an M cross N matrix. Is that okay? What are the elements of TAB? So the elements here are, look at elements of A. Elements of A are V1, V2, Vn. All right. Write them with respect to B and close it. So this is what your T of A of B is. Fine. So I would like you to understand them nicely. Fine. Let us take some examples. All right. So I will not go like this. I will do it in a different way. So let T be so let T from R to R, T from R2 to R2 be the counterclockwise, be the counterclockwise rotation by an angle theta. Then what is the matrix of T with respect to ordered basis E1, E2 of R2. All right. So what exactly we need to do? We need to compute. So if I want this matrix T, so ordered basis I will not write anything. Here I wrote T of AB, so this will indicate it is T of, so if I write this as B, T of BB, because I am going from R2 to R2 itself, so BB itself. So what I am supposed to look at T of E1, I am supposed to look at T of E1 with respect to B, T of E2 with respect to B. This is the matrix that I am going to look at. This is what we saw. T of V1, T of V2, T of Vn. So T of E1, T of E2 and with respect to B. So what is this? So let us go back here. I have the vertex here as 1, 0. This is my E1. Fine. Now if I rotate it by angle theta counterclockwise, this is my theta, then this point will be cos theta sin theta. Fine. So therefore this vector in the basis B, what is the basis B? A standard basis itself, it is nothing but cos theta and sin theta. Fine. The second vector is E2. So this is my E2, which is my 0, 1. I would like to rotate it by angle theta here. So what is this vector? Fine. So if this vector is theta, so this is nothing but pi upon 2 minus theta, and therefore this vector is, so if I look at this, the x component here is this part, fine, which is negative here, and it is nothing but cos of this, and cos of this means it is minus of sine of this. So it is minus sine theta because cos is negative in this component. Fine. Similarly, the vertical component will be sine of this. Sine of this is same as cos theta. Fine. So this vector is nothing but, complete it yourself. Again see, x component I am looking at. X component is negative because this is the origin is negative. This is the angle pi upon 2 minus theta. So it is cos of this. Cos of this is nothing but sin theta with a negative sign. So I get minus sin theta, and similarly I will get cos theta here. All right. So overall, if I want to see, it is pi minus theta, but I am just looking at this part. So this is pi by 2 minus theta, so I get this as the matrix. Is that okay? So you can easily see that if I had wanted to compute T of xy for a general setup, it would have been a big job for me, because I'll have to look at any point xy here, rotate it by angle theta, and then find out the coordinates would have been difficult. But in place of looking at any xy, it says that I just have to look at a standard basis, and when I am looking at a standard basis, E1 and E2 is the standard basis for me, or any basis as such, and I could do it. So just verify that, verify T of xy, since I am looking at a standard basis, it is nothing but cos theta minus sin theta cos theta times xy, which is nothing but x cos theta minus y sin theta and x sin theta and plus y cos theta. So I would like you to verify that these points are same. The point here and the point here, they are the same. Is that okay? You can do it differently also, but that's the way we do it. Fine. One more example, or I will do the next example in the next class. All right. Thank you.